Hi there, this is Group 15, and this is our surface mount reflow solder oven. So what this oven is for is to take PCBs, in fact our oven can accommodate 9x9 size PCBs, and melt the solder on them for surface mount components. So with this you can have generic profiles for leaded and unleaded solder, as well as even some customized on your own profiles. So I guess without further ado, we'll look into further details of this oven.
This is our block diagram for the surface mount oven project. The core of the project is the microcontroller that handles all user input, status displays, and heating control. The entire project runs from a standard wall outlet. It has a power supply that takes 120 volts AC and converts it to 12 volts DC for the microcontroller to use. The microcontroller takes user input, whether it be uploading a standard generic profile that we have on there for leaded and unleaded, or a custom profile where the user can set dwell and peak temperatures. That profile is then initiated by turning on heating control, which is a mechanical relay that controls whether or not power is allowed to flow through the heating elements. Inside of the oven we have 4 heating elements drawing a total of 12 amps to power the heating of the PCB. There are 4 heating elements evenly spaced throughout the chamber of the oven that help provide a nice even heat flow. The temperature sensing is accomplished by K-type thermocouples located inside of the chamber. These K-type thermocouples produce about 40 microvolts per degree C, which is amplified by about 30 decibels by op-amps inside of the sensor block powered by the microcontroller. This temperature measurement is then fed into the microcontroller and used to display the current status of the oven.
Jonathan Furno, and I did the microcontroller hardware and the microcontroller software. As you can see, if you look at the display, you can look to see each the options that I had. So the way that you do a profile is you just click run, one button to go through the run option, and then there's 2 profiles that are pre-made, the leaded and unleaded option. You can go back to the menu, and now I'll show you the ability to select different dwell times and peak temperatures in the microcontroller. You can see the time, and you can see which place value that you're changing at this point. So I can change the 1, I can make it go up 1, make it go down 1, and then I can be done with it. In the hardware, this is the other part I did, we have some of the inputs coming in through this wire to one of the ports. We have some of the outputs to the different lights, and we have the output to the screen. So one of the unique design considerations that we had for the microcontroller aspect of the surface mount oven was that we are having interference, magnetic interference, through some of the power and some of the signal wires. And so how we overcame this with the software side was we took the best out of 2 of 3 of the measurements. We took a fake measurement before each real measurement, and then we also took 19 individual measurements from the best 2 out of 3. So we threw out a lot of bad data, and through the law of averages we just eventually came up with some good readings, and we're able to display the real-time temperature from the oven every second. And that was one of our unique design challenges.
For our project, I worked on the oven body and the power supply. So you can see from the oven body, we actually bought a toaster oven from Body-Mart and gutted all the electronics out of it. Instead, all we kept was the oven body itself and the heating coils. So for our oven, we actually run off a standard 120 volt outlet. And in fact, the elements, we chose elements that will run off 120 volts. So they are 120 volt AC elements. For our oven, it's controlled by just a front switch, and when you turn this on, the 120 volts is connected to an internal power supply that converts 120 volts to 12 volt DC at 10 watts, which supplies the microcontroller and all the other low voltage components up here. All the high voltage components are isolated inside here in the oven. So to control the heating elements inside our oven, the microcontroller, which is powered by a 12 volt supply, has a pin that outputs 4.7 volts at a very low current. So what it does, it sends out a 4.7 volt signal, which then connects to a MOSFET. That MOSFET triggers and allows 12 volts to a mechanical relay which controls the elements. The mechanical relay is one just actually like this one. So with a mechanical relay, as soon as you apply 12 volts across the coil, it'll activate the relay and allow 120 volts and 12 amps through the heating elements. In order to turn off the elements, all the microcontroller has to do is remove that 4.7 volts. Then the base of the MOSFET is tied to ground, which turns off the MOSFET and in turn turns off the voltage to the coil of the relay, thus turning off the entire oven.
Hi, my name is Greg Hendrickson. I was mainly responsible for the temperature sensing of the surface mount oven that we were working on. The temperature sensing is handled by K-type thermocouples that are connected inside of the chamber of the oven and run up through the low voltage housing. The thermocouples report approximately 40 microvolts per degree Celsius of temperature and are usually more accurate at higher temperatures. The thermocouples are then tied into amplifiers, so we need to amplify the low voltage signal being supplied by them to the microcontroller. The amplifiers amplify the signal by approximately 365, which corresponds to a gain of about 30 decibels. That's easily within the 120 decibel limit that the op amps provide. The input offset voltage of the op amps is approximately 150 microvolts to help minimize the error, which corresponds to approximately plus or minus 4 degrees C in error reporting. But the expected value of that input offset voltage is approximately 80 microvolts, which corresponds to about plus or minus 2 degrees C, which helps our temperature accuracy requirement. The op amps then report that output voltage to the microcontroller, which can then use it to match the heating profile selected by the user.
So here we have a demonstration of our surface mount oven in action. So in order to run the surface mount oven, all you need to do is turn it on, which brings up the menu. We're going to run through a leaded solder profile. So choose Run, and we're going to select the leaded solder profile. So if you see the star there, selecting it, click Run. So we're measuring the temperature inside now. As you can see, there's a little bit residual temperature inside, but what this will do is it turned on the relay inside the oven. See, the heating coils now are beginning to heat up. So as you can see, we are starting to approach the temperature. On the menu, the middle temperature is 150 degrees Celsius, which is our dwell temperature. So once we hit 150 degrees Celsius, we will sit there and allow a drying period for the PCB, removing any moisture. And right now on the far left is 134 degrees Celsius. So that's the actual air temperature inside the oven. So as you can see, this thermometer lags behind the actual temperature, but it is actually reaching that temperature. So we hit 150 degrees Celsius. If you could hear it, the relay clicked off. So the elements are now off, and the temperature will climb a little bit more and then begin to drop as the inside of the oven begins to cool. So now after the dwell period, we will begin moving towards our max temperature. So the relay clicked on. Temperature is beginning to climb again, and we're now shooting for 250 degrees Celsius. Okay, as you can see, we are approaching our peak temperature. So inside about 500 degrees Fahrenheit. So we're at our peak temperature, and once we hit our peak, the relay clicked off, our coils are now turning off, and the oven will cool, and we are now back at the main menu. So this concludes our demonstration of the surface mount oven during a leaded profile. A few tips for the starting senior design. One of the most important things to do is to make sure you have extra parts for when things go wrong. Even if you have extra parts, make sure you have access to even more extra parts when those blow.
And my advice would be to get a generic schedule worked out so that you don't have to rush order any parts, because overnighting parts can add up a lot, up to $30 to $50 for some different items.
My advice for students taking the class would be to make sure you get a group you know you can work well with, not necessarily a group of friends, although in this case it did work out great, but make sure that they know there's a team involved and that there's going to be accountability. They need to get their work done. And the second thing is to try to set realistic goals for yourself, especially in the first term, because you don't know what problems you're potentially going to encounter when you actually start building it in winter term. So make sure you research your goals and talk with your mentor or supervisor and make sure you set yourself realistic goals that you can attain.
All right, thank you.